Okay, so in this video, we will use the monotone convergence theorem to prove that the sequence Sn converges by proving that it is increasing and bounded. So we will first start with increasing, as it is the simpler one to show. So let's expand this summation just to get a feeling for what Sn is, right? When we have a summation, it's always more intuitive in expanded form and not in sigma notation. So when n is 1, we get 1. Then plus when n is 2, 1 over 2 squared. Plus when n is 3, 1 over 3 squared. Plus when n is 4, 1 over 4 squared. Plus dot 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 up to the very last term when lowercase n equals uppercase n, in which case we get 1 over uppercase n squared. So to show that this sequence is increasing, we will show that Sn plus 1 is larger than Sn. So well, what is Sn plus 1? Well, it is the summation as lowercase n goes from 1 to now no longer uppercase n, but uppercase n plus 1. So let's expand this. Again, n begins at 1. So we get 1 over 1 squared, which is 1. Then plus, when n is 2, 1 over 2 squared. Plus when n is 3, 1 over 3 squared. Plus 1 over 4 squared. And continues to increase. 1 over n squared. And finally, after n is uppercase n plus 1, so we get 1 over uppercase n plus 1 squared. And if you notice, in Sn plus 1 is Sn. So this is simply Sn. The sum of the first n terms is exactly Sn plus a positive term, 1 over n plus 1 squared. So as Sn plus 1 is Sn plus something positive, it clearly is larger than Sn. So we have an increasing sequence. From n to n plus 1, Sn plus 1 is larger than Sn. So the next term is larger than the previous term. And if you think about this, this is fairly obvious. If you look at the sequence and where n is the upper bound of summation, and we are summing positive terms. So as n increases, we are summing more and more positive terms. Therefore, the summation gets larger and larger every time n increases. So it's clear that because we have a sum of positive terms, that the more terms we sum, the larger the sum gets. So we have obviously an increasing sequence, but here we did demonstrate this fully. So now the first half is done. The sequence Sn is increasing. Part 2, let us now show that the sequence is also bounded. Now, one obvious remark is that it is clearly bounded below. If you're summing positive numbers, the result can never be smaller than 0. And in fact, the first term when n is 1, the sum is simply 1. So the sum is always at least as big as 1. So we now have a lower bound of 1 for any n. The summation will always be at least as big as 1. Now we need an upper bound. And this is the step that's a bit more interesting. What we will do is find a way to compare Sn, the summation, to the area under a curve. And since we're summing 1 over n squared, it seems plausible that we could compare the summation to the area under the function 1 over x squared. And since we're summing at integer values of n, we are only interested in positive integer values of x. And we're going all the way up to n. So our last point we'll consider will be uppercase n, and of course before uppercase n is uppercase n minus 1. And now what's interesting is we have intervals of width 1 in each case. So let's construct now rectangles whose area will be exactly the area of each term of this summation. So let's look at the area of these rectangles. Again, the y values are 1 over x squared at any given point, and the width is 1. So the area of the first rectangle will be 1 times 1 over 1 squared, which is 1. So the area of the first rectangle is 1. The second rectangle, it is again 1 times 1 over 2 squared. It is 1 over 2 squared. Third rectangle, base 1 times the height, 1 over 3 squared. Fourth rectangle, 1 times 1 over 4 squared. And finally, the last rectangle, and here I'm a little bit out of space, so I'll include it like this. The width of our rectangle is 1, the height is 1 over n squared. So we can now picture Sn as the total area of these n rectangles. And now we can compare the area of those rectangles to the area under the curve y equals x squared, and it is clear that the total area of the rectangles will be less than the total area under the curve. For each rectangle, we're missing a little portion of the total area below 1 over x squared. But as we have a singularity at x equals 0, where the function blows up to infinity, we will leave the rectangle, the first one, on its own, and only compare the rest of the summation to the area below 1 over x squared. So now this is the area in total of all of the other rectangles except for the first one. So this will be at most the exact area under 1 over x squared from 1 all the way up to n. And so what do we have now? Well, the summation therefore is, we'll keep 1, so smaller than 1, plus the larger quantity, the integral from 1 to n of 1 over x squared with respect to x. This is now a very simple integral to evaluate. We can use the power rule to find an antiderivative. So this is x to the negative 2. Power rule gives us x to the minus 1 over minus 1, which is negative 1 over x. And we of course evaluate from 1 to n. This will give us, so 1, the antiderivative at n, negative 1 over n, then minus minus, so plus 1 over 1 plus 1. So the result is simply 2 minus 1 over n. And now it should be clear that as n is a positive integer, if you remove a little bit away from 2, the result will always be smaller than 2. So we now have an upper bound for our sequence. For any n, Sn is always smaller than 2, and we did show that Sn was also at least as big as 1. So we now have the two conditions met. So we did show in the beginning that Sn was increasing. Since we did show that Sn plus 1 is strictly bigger than the previous term Sn, and we now have just shown that Sn is bounded above by 2 and below by 1. And this is true for all values of n. So, we can now quote the monotone convergence theorem. If a sequence is increasing and bounded, it converges. So by the monotone convergence theorem, Sn converges which is of course a fancy way of saying that the limit of the sequence exists. So is equal to say L, where L is an actual positive real number. And let's now rewrite this in summation form. Sn was the summation, as lowercase n goes from 1 to uppercase n, of 1 over lowercase n squared. And now we can write this even more concisely, right? As uppercase n tends to infinity, we can write this summation in the same way we would an improper integral. We can write this as the sum as lowercase n goes from 1 to positive infinity, as we are letting the upper bound of the summation tend to infinity, of 1 over n squared. And if we expand this infinite sum, which we know must converge to some positive real number, we get a very interesting result. So 1 plus 1 over 2 squared, plus 1 over 3 squared, plus 1 over 4 squared, plus 1 over 5 squared, and so on. And again, because the upper bound of summation now is infinite, this sum never ends. It is a sum of an infinite number of positive terms. We can write this, if we evaluate these squares, so we get 1 plus 1 quarter, plus 1 over 9, plus 1 over 16, plus 1 over 25. Let's add one more, 6 squared, 1 over 36, and so on. And so with the help of the monotone convergence theorem, we were able to show now that this infinite series does converge. And I'll leave you with a small extra piece of information. Not only does this converge to some positive real number, but this number happens to be exactly pi squared over 6. And this is, I think, fairly surprising.